right, so we're going to be going over some of the concepts that we were talking about prior to spring break. I've got 5 review problems to go through today. I think that they should go pretty quickly. All right, so let's kind of jump right in. Oops, not what I meant to do. All right, so the first problem, we've got water flowing with a Q of 10 cubic meters per second and a rectangular channel with a B of 3 meters, a bottom width of 3 meters. And we're asked to determine the Froude number and the type of flow for depths of 30 centimeters, 1 meters, and 2 meters. And then we're asked to specifically find the critical depth. All right, so here we are given Q equals 10 cubic meters per second. B is equal to 3 meters. And then Y is equal to either 0.3 meters, 1 meter, or 2 meters. We're also being asked to use our Froude's number, where a Froude equal to 1 corresponds with our critical flow depth. This is the depth of water that minimizes the specific energy in a channel for a given channel geometry and flow rate. When we have Froude's number greater than 1, we are in our supercritical flow regime. This corresponds with fast, shallow flow. And a Froude's number of less than 1 tells us that we are in our subcritical flow regime, where we have deep, slow flow. So Froude's number is given to us in terms of velocity as just the velocity divided by the square root of the acceleration of gravity g times the water depth y. For situations where we do not know the velocity, we can substitute in Q divided by A for our velocity. And for a rectangular channel where our A is going to be equal to B times Y, we can make another substitution here. If we simplify all of this down, we can put our volumetric flow rate Q on the top. Let's fix that. And that whole thing would be divided by, if we drop this B down here, times the square root of the acceleration of gravity, and then multiplying y times the square root of y gives us y to the 3/2 in the denominator there. So we need to find this Froude's number for 3 different values of y, which are given up here. So first, our Froude's number, when we have a y of 0.3 meters, is going to be equal to our volumetric flow rate of 10 cubic meters per second divided by our bottom width of 3 meters, the square root of our acceleration of gravity of 9.81 meters per second squared, and then our given water depth of 0.3 meters to the 3/2. We calculate all of this out, we should get a value equal to 6.48, which is associated with a supercritical flow, because we have, again, a Froude's number greater than 1. If we calculate our Froude's number for a flow depth of 1 meter, everything looks about the same, 10 cubic meters per second. Flow depth or channel width of 3 meters, acceleration of gravity of 9.81 meters per second squared, but now a y of 1 meter. We end up with a Froude's number that is approaching our critical. It's almost 1. It's slightly greater than 1, but we're getting a little bit closer. And now if we try this again for a flow depth of 2 meters, so Q is the same, B is the same, G is the same, and now we're looking at a depth of 2 meters, we end up with a Froude's number of 0.36, which is going to be associated with our subcritical flow. The next part of this question asks us to find what is the critical depth. And we know from our lecture notes that simplifying Froude's equation, substituting in 1, and then assuming a rectangular channel geometry here, that for rectangular channels, our critical flow depth, here denoted by YC, can be approximated by taking our little q squared divided by the acceleration of gravity and raising that to the 1/3 power. Since little q is equal to big Q over B, we can also write our critical flow depth equation like this. If we substitute in 10 for our Q2, 10 for our Q, 3 meters for our B, and the acceleration of gravity, we end up with a YC of 1.04 meters, slightly greater than the 1 meter that gave us a critical flow depth of close to 0.1. Okay. All right. Now let's go on to problem 2 here. So now if we're going back into our previous channel, this should be a 3, where we have our same volumetric flow rate and our same channel geometry with a B of 3 meters from problem 1. We're asked to find the alternative depth to a 30 centimeter depth. So if you will, so here we are given Q equals 10 cubic meters per second, B equals 3 meters, Y equals 0.3 meters. We want to find, I'm going to make this Y1, we want to find Y2. And if you will recall, if we take our specific energy, which is equal to the depth of our water plus our velocity head, and we plot that against the water depth, y, we can draw a curve in this space for any given q such that one specific energy will be associated with 2 possible flow depths. The smaller y is associated with the supercritical flow, and the larger y here is associated with the subcritical flow. So we know that from the previous problem that this y of 0.3, our smaller y, is associated with the supercritical flow. So what we're being asked to find is the subcritical flow depth associated with that same specific energy and that same volumetric flow rate. So what we know here is that our E1 is going to equal our E2, which means that our water depth and velocity head should be equal across these 2 points here. And so if we solve for E1, where we have a depth of 0.3 meters, and then if we substitute in we write our velocity head, and I'm just going to circle this here. So we can write our velocity head in terms of the velocity, but we can also write it in terms of our volumetric flow rate. By using this value little q here, which is our volumetric flow rate, big Q standardized by the bottom width of the channel B. So we know here that that's going to be volumetric flow rate 10 divided by 3. And this whole thing is going to be squared times 0.3 squared times 2g. And that's going to be equal to our y2 plus our little q plus y2 squared times 2 times 9.81. And we end up in a situation where we have an objective function. So this all here simplifies to 6.59 meters is going to be equal to y2 plus 10 over 3 squared divided by y squared times 2 times 9.81. So this is your objective function. And you can plug this into a solver to get a second value of y2. But, I'm going to put a little asterisk here, you're going to have to guess an initial value of y2 that is greater than our subcritical or our supercritical flow depth that was calculated during y1. Otherwise, this will just return y1. If you have any questions on how to do that, just let me know. All right, problem 3. Same exact kind of a problem, but again, getting a little bit more creative with toggling between big Q, little q, and velocity here. So we're given a flow depth y of 10 centimeters and a velocity v of 6 meters per second in a rectangular channel. First question is we need to figure out is the flow subcritical or supercritical? And then the second question is, again, we need to find this alternative depth. So for the first part of the question, we just need to check our Fruit's number. And here, since we're given a y and a v, we can write our Fruit's number in terms of y and v. So that would be 6 meters per second divided by the square root of 9.81 meters per second squared times 0.1 meters. We'll try to be consistent with either using or not using units here. Ooh, it's a little bit bigger of an eraser than I was hoping for. And if we plug and chug everything here, we should end up with a Fruit's number of 6.06, meaning that our flow is supercritical. The reason why this matters is that the alternative depth to a supercritical flow regime is going to be higher than the water depth that we were originally given of 0.1. So the same thing as before, to find this alternative depth, We want to make an objective function out of our conservation of energy and use that objective function to find an alternative value of y. So since E1 is going to be equaling E2 again here, we're going to end up with y1 of 0.1 meters is going to be, needs to be a plus sign, plus our velocity squared divided by 2 times the acceleration of gravity is going to have to be equal to y2 plus v2 squared times 2 times the acceleration of gravity.